Hello everyone, welcome to the Gate Wallah. So good evening everyone, very good evening to all of you. So on Monday, I started the fault analysis in the power system and I told you we can classify fault into the two categories. It may be the series fault and the shunt fault. We will be focusing our discussion only about the shunt fault. The shunt fault again can be classified into two categories. One is the symmetrical fault and second is a unsymmetrical fault. If all the three phases are involved into the fault then it is a symmetrical fault. If only one phase or two phases are involved, then such type of fault is called the unsymmetrical fault. So we have done the analysis of the symmetrical fault as well as the unsymmetrical fault. That means how to find out the fault current when the three phase fault occurs, when line to ground fault occurs, when line to line fault occurs, and when double line to ground fault occurs. Now, in this class, we will try to solve some question and we'll find out the fault current for the different nature of fault. So let's start. So this was the recap of our previous class, what we have done in the yesterday class. I solved some question that is based on the line to line fault. Then I have done the analysis for the double line to ground fault. The motive and the aim of today class, we will do the question practice for symmetrical fault as well as for the unsymmetrical fault. So let's take example. This is a question. What will be the sub-transient fault current in each phase for a dead short circuit in the one phase to ground at the bus Q? See, it is having two bus, P bus and the Q bus. Bus will be here, see. The bus will be this side. So this is a Q bus. P bus and the Q bus. Or let's take Q bus here only. I will check out whether it may be this side or this side. So I'm taking this as a Q bus only. Okay. So when line to ground fault occur in the bus Q, then what will be the value of fault current? So this is a alternator, then again bus P, a transformer, a transmission line, a bus Q, then transformer and the transmission line. Actually, generally we do not take bus here. So let me change this question because we always have bus at the generator side. So let's take this is a Q. According to that, we will change the option. Clear? So this transformer is connected in the delta star grounded, then star grounded and delta. Let's. So how to solve this type of question? See, when line to ground fault occur into the system, then not only the positive sequence current, but the negative sequence current as well as the zero sequence current is also flow. So we will draw the positive sequence network, negative sequence network and the zero sequence network. And we'll find out the equivalent positive sequence Thevenin impedance, negative sequence Thevenin impedance and the zero sequence Thevenin impedance. So let's draw first the positive sequence network of the given circuit. Positive sequence network. Now, how to draw the positive sequence network of the overall circuit? Just draw the positive sequence network of the individual component. So first is a alternator. So alternator positive sequence network is nothing but a source in series of a positive sequence impedance of alternator, and that is the sub transient impedance J 0.16. So it is a J 0.16, 1 angle 0 degree. So it's a PSN, or the positive sequence network of the alternator. Now after this alternator we have a transformer. The positive sequence network of the transformer is nothing but a reactance whose positive sequence reactance value is J 0.10. J 0.10. Now next, again we have a transmission line. The transmission line positive sequence reactance is J 0.33. J 0.33. Then again a transformer. The transformer positive sequence network is nothing but a reactance of value J 0.10, J 0.10. Now again we are having a synchronous machine. Synchronous machine, the positive sequence reactance is, positive sequence network is a reactance and a source, 1 angle 0 degree, and positive sequence reactance of this is nothing but the J 0.2, J 0.2. Now where the Q bus is located? Here, after the transformer. So I am taking the Q bus is here. This is our Q bus and the fault takes place here. Now just find out the Thevenin equivalent positive sequence reactance at the fault point. So to find out the Thevenin equivalent reactance, we will turn off the sources. Here we have a 2 voltage sources. Turn off the voltage sources. Now find out the Thevenin equivalent reactance at this point. So 0.16, 0.10, 0.16, 0.10, this means it is become 0.26. 0.26 and 0.33, it's a 0.59. So it has become 0.59. And here 0.1, 0.2. So J 0.3, J 0.3, 0.2, 0.1. Now the overall reactance here, X1, what will be its value? The 0.59 and the 0.3, they are connected in parallel. 59 and 3, that is the 89. Now calculate this value. .59 into 0.3 divide by 0.89, 0.1988, 0.1988 J. This is the Thevenin equivalent positive sequence reactance at the fault point. Now, in the similar manner, just find out the negative sequence network. So let me draw the negative sequence network. Negative sequence network. The negative sequence network does not have any source. So for alternator, the negative sequence network is nothing but a reactance, and its value will be negative sequence J 0.17, J 0.17. For transformer, again it's a reactance, its value is 0.10, J 0.10. Then for the transmission line, again it is a reactance, and the negative sequence reactance of transmission line is J 0.33, J 0.33. second transformer J0.10, J0.10, and then synchronous machine. The negative sequence net of the synchronous machine is nothing but a reactance, and the reactance value is the J0.22, J0.22, J0.22. Oh, I have done one mistake because the Q bus bar is after the transformer. So here we have after the transformer. This Q was located after the transformer. So I have to recalculate this. This was the Q. This was my Q point. So this is 0.2, J 0.2, 0.26, 0.33, 0.59, and 0.10, 0.69. So X1 will be 0.69 into 0.2, 0.89. 0.69 into 0.2 divided by 0.89, 0.155. Clear? Okay. Now the negative sequence network. Here we have a Q. So find out the Thevenin equivalent negative sequence reactance. So the total value is 0.43, 0.43 and 0.17 is nothing but the 0.70, 0.60 and this 0.70. 0.70. Now this is J 0.22. So X2 is 0.70 into 0.22, 0.92. Calculate this value. .70 into 0.22 divided by 0.92, 0.1674 is the Thevenin equivalent negative sequence reactance. Now find out the zero sequence network. Take care while drawing the zero sequence network of the three-phase transformer. First, the zero sequence network for the alternator, it is nothing but the 0.06. So first is the 0.06, J 0.06. Now come to the transformer. The transformer connection is delta star. I told you this is our circuit for drawing the zero sequence network of a transformer. Primary side is delta, so this will be connected. Secondary side is a star with the ground, so this will be connected. So it will be like this. It is like this. Clear? So it will be like this. Sorry, delta. Like this. And its value is the J 0.10. 0.10. Clear? Now, transmission line is represented as a reactance and its value is 0.33, J 0.33. Now, again, a transformer. Now here, this is star connected. That means this switch will be closed and this switch will be closed. So it will be like this. It will be like this. So it will be like this. Like this. This is the circuit. And it's this reactance value is 0.10 and finally this is the 0.15. J 0.10 and finally J 0.15. Clear? So where is the Q? The bus bar Q is after this transformer. That means here we have a bus bar Q. We have a bus bar Q here. This is a bus bar Q. So this find out the impedance here. What is the impedance here? Yes. What is the value of impedance here? This point is a Q. So impedance here is, this is my open circuit, only the 0.15 is there. So 0.15. So X naught is nothing but the 0.15. 0.15. Clear? Now, once you got the value of x1, x2 and x naught, you have to find out the value of fault current. So the value of fault current, okay, for the line to ground fault. For line to ground fault, what is the value of fault current? It is nothing but the 3E x1 plus x2 plus x0. Clear? Now, the fault current is the 3, x1 is 0.155, 0.1674, 0.155, 1674, 0.15. So the value of fault current is this. 3 divided by 0.155 plus 0.1674 plus 0.15 It is nothing but 6.35 minus j 6.35 pu. So this is the value of fault current minus j 6.35. You have to change here because I just changed the location of Q. $6.35. Clear? So this is the right option. Any doubt here? Okay. Now, if line to line fault occur in the same circuit, then what will be the value of fault current? Again, first we will draw the positive sequence network and the negative sequence network. And now we know what is the fault current for the line to line fault. It is nothing but the root 3E divided by x1 plus x2. Just put the value of x1 x2 because by drawing the positive sequence network and the negative sequence network, we have already find out the Thevenin equivalent positive sequence reactance and the Thevenin equivalent negative sequence reactance. So root 3 into 1 x1 plus x2. x1 was 0.155, 0.1674. 1551674. Calculate this value. Under root 3 divide by 0.155 plus 0.1674 minus j 5.372 pu is the right answer. 5.372 is the right option. Five point 372 pu is the right option. Clear? Okay. So in this way you can solve this type of question. Okay. In the same question, when the line double line to ground fault occur and the no fault impedance is there, then what is the value of fault current? So how to solve this? We have the x1, x2, x3. Then how to solve this? See, I told you yesterday, the overall circuit will be like this. Positive sequence, negative sequence, and the zero sequence. ZF is 0. So it is x1, this is x2, x0. XF is not there. See, this is my IA1, this is IA2, and this is IA3, IA0. The fault current is equivalent to IA0. Yesterday I told you. So, how to get the value of IA1? First, I will find out the X equivalent of X0 and X2. So, just find out the X equivalent, which is X0 into X2, X0 plus X2. X0 into X2, X0 plus X2. The X0 is X2 is 0.1674, 0.1674, and X0 is 0.15, 0.15, yes, 0.15. Now 0.1674 plus 0.15. 0.08 pu. 0.08 pu. This is X equivalent. So IA1 is the 1 angle 0 degree X1 plus X equivalent. So IA1 1 angle 0 degree X1 plus X equivalent. This is IA1. So 1 angle 0 degree 0 point X1 is 0.155 155 plus X equivalent is the 0.08. This is our positive sequence current in case of double line to ground fault occur. So 1 divided by 0.155 plus 0.08, which is minus J 4255 pu. This is IA1. Now, from current division rule, you can find out the value of IA0 from current division rule. Current division rule, this current is a negative of this. IA1 will divide between the X2 and X0. So, the current division rule, IA0 is the negative of IA1, X2, X0 plus X2. How much current coming out from the X0 branch? So, J 4.255 into X2 1674 0.1674 and X0 is the 0.15 plus 0.1674. You will get this value of IA0. So IA0 is become 4.255 into 0.1674 divided by 0.15 plus 0.1674. 2.24 in magnitude. It is a 2.244 pu. Now, the fault current is the 3 times of IA0 multiplied by 3, 6.73. 6.732 pu is the right answer. 6.732 is the right answer. So C is the right answer. So by using one example, I show you how to find out the fault current when the line to ground fault, 3-phase fault, line to line fault, or the double line to ground fault occur. First, you have to draw the positive sequence network, negative sequence network, zero sequence network. Then find out the Thevenin equivalent positive sequence reactance, negative sequence reactance, and the zero sequence reactance. Then by using the formula of line to ground fault, line to line fault, or double line to ground fault, you can easily find out the value of fault current. Clear? This point is clear? Okay. Now I move to the next question. See, in this question, a system is having the 4 alternator, each rated at the 11 kV and the 50 MVA. And the sub-transient reactance of each alternator is the 15%. What should be the value of current limiting reactor to limit the fault level to 800 MVA. If fault occur here, if the fault is occurring here, then the fault MVA should not be more than the 800 MVA. So first I will take the rated quantity as a base quantity, means the 11 kV and the 50 MVA I am choosing as a base voltage and the base MVA. So base voltage 11 kV and the base volt ampere is the 50 MVA. Clear? From this we can find out the base impedance kV square upon MVA. kV square upon MVA. So 11 square divided by 50. 121 divided by 50. 2.42. 2.42 ohm is the right option. Clear? Now, sorry. Now the fault occur here, the reactance of every is the 0.15, J 0.15 on the same base, J 0.15, J 0.15. This fault MVA for the three-phase fault, always remember. So at this bus bar, the fault occur. So J 0.15, J 0.15. If I draw the positive sequence network, this is the positive sequence network of alternator number 1. It's a zero potential bus per phase. Similarly, for second alternator also, every alternator is having the reactance of 0.15. Now they are connected by a bus. Again 0.15, 0.15 for the remaining two alternator. This is the positive sequence network, zero potential bus, J 0.15, J 0.15. There is a reactor whose value we have to calculate. Now zero potential bus are the same, that means they are at the same potential, means you can say they are connected together. They are connected together. Now the fault is occur here. This is the fault location. Now the Thevenin equivalent impedance is nothing but the overall impedance between the zero potential bus bar and the fault location. So I find out the overall reactance here. So 0.15 and the 0.15, they are connected in parallel. So their overall values become 0.15 divided by 2, 0.15 divided by 2, 0.075. So it is become 0.075, 0.075. This is 0.075. Now at this location and this location, the Thevenin equivalent reactance XTH 0.75, 0.075 and X are connected together. So 0.075, 0.075 plus X. Sum of these two, 0.15 plus X. This is the Thevenin equivalent reactance. Clear? Now, here the fault MVA is given. So what is the fault MVA? I told you the fault MVA in term of PU value is nothing but the 1 upon XTH. But in term of actual value, the base MVA divided by XTH. So fault MVA is 800 MVA and base MVA is a 50 MVA. 800 MVA, 50 MVA into XTH. So XTH is become 50 upon 800. One upon 16. In term of Pu value. This is in term of Pu value. Clear? So XTH is the 1 upon 16. Now 1 upon 16 is equivalent to 0.075, 0.075 plus x, 0.15 plus x, and then find out the value of the x. So 16 into 0.075, 1.2. So 1.2, 0.075 plus x, 0.15 plus x. Zero 0.09 plus 1.2x, 0.15 plus x. So it is a 0.2x, 0.15 minus 0.09, 0.06. So value of x is 0.06 divided by 0.2, 0.3 in term of Pu. See, this is in term of Pu. X is this in term of Pu. Now what is the value of actual value? So actual value you can find out the Pu value into the base value. Actual value is the 0.3 and the base value 2.42. 2.42. 2.42 multiplied by 0.3. 0.726 in term of ohm. 0.726 in term of ohm is the right option. Clear? So what was the method? First draw the positive sequence network. See, choose the base voltage, base kVA, find out the base impedance. Now the fault MVA is the base MVA divided by XTH in term of Pu value. So base MVA is given, fault MVA is given. This is the XTH in term of Pu value. From this positive sequence network, find out the XTH, which is nothing but the equivalent impedance at zero potential bus and the fault location. You will get this value. Now equalize these two XTH and get the value of X. This is the Pu value. So convert this X into the actual quantity. So 0.3 into 2.42, 0.726 is the right option. Okay, let me take one more example. Okay, let's take this example first. A 36.6 kV alternator having the rating of 8 MVA, 2 MVA and the 5 MVA have the Pu reactance of 0.16, 0.08 and the 0.12 respectively are connected to a bus bar. A three-phase feeder which take off from the bus, the reactance of the feeder from the bus to the fault point is the 0.125 ohm. What is the fault MVA? See, first draw the single line diagram. We have a three alternator. Everybody the 6.6 kV, but MVA is a different. It is a 8 MVA. Second one is a 2 MVA. And third one is a 5 MVA. The reactance is given. The reactance is this, is the J0.16, J0.08, J0.12. They are connected to a bus bar, a three-phase feeder which take out from the bus. Now, a feeder is coming from this bus. The reactance of feeder from bus to the fault point, suppose here the fault occur, is the 0.125 ohm. What is the fault MVA? The three-phase fault MVA. Until unless it is mentioned, it is called the three-phase fault MVA only. So you can see the rating of all the alternator is differ. So first you have to choose one base MVA. So let me choose base voltage. Voltage are the same. It is a 6.6 kV. So I will taking the 6.6 kV as a base voltage and the base volt ampere. The base volt ampere I am choosing as a 8 MVA. As a 8 MVA. So from these two I can find out the base impedance kV square upon MVA. kV square upon MVA. So it is a 6.6 kV square divided by 8 MVA. 6.6 square divided by 8. $5.445. 5.445 is the ZB, the value of ZB. Now what I will do, I will convert all the reactance into the base value. So let take this alternator number 1, alternator number 2, alternator number 3. So reactance of alternator number 1, 𝐂𝐸1. It is already on the 8 MVA, so it is the J0.16. J0.16. Reactance of alternator number 2 on the new base is the 8 MVA. 0.08 is on the 2 MVA. So J0.08 on the 2 MVA. Now at the 8 MVA it will be J0.32. Similarly, the reactance of third alternator, it is on the 5 MVA, it is a 0.12. 0.12 on the 5 MVA. At 8 MVA, what will be its value? 0.12 into 8 by 5. $0.192. 0.192. Clear? Now, I also convert this into the Pu value, 0.125. So, the Pu reactance of line, transmission line Pu reactance, actual value divided by base value. Actual value is the 0.125, 0.125, and the base impedance I just find out 5.445. 5.445. Clear? 0.125, 5.445. It is nothing but the 0.023 pu. 0.023 view. Now, let's draw the positive sequence network for one alternator, for second alternator, and for third alternator. And this is a fault point. All have the zero potential bus, so they will be connected together. Find out the reactance between the fault point and the zero potential bus. 0.16, 0.36, 0.32, 0.192, and this is 0.023. So these are in the parallel. Point 0.16, it is a 0.16. Zero 0.16, 0.32, 0.48, 0.1067, and now 0.192. So 0.1067 into 0.192. 0.1067 into 0.192, 0.1067 plus 0.192, 0.0685. Now 0.0685 plus 0.023. 0.09158. Now you have to find out the fault MVA. So fault MVA is nothing but the base MVA divided by X. So fault MVA base MVA divided by X. The base MVA is chosen 8 MVA, 0.09158. 8 divided by 0.09158. 87.35. 87.35 MVA is the right option. Clear? 87.35 is the right option. This. So here, because the rating of every alternator was different, so first you have to choose the one base and convert all the reactance into that base only. Then find out the overall reactance between the fault point and the zero potential bus bar. The fault MVA is nothing but the base MVA divided by X. Clear? Okay. So in the 6 classes, I have given a brief idea about the fault in the power system. I told you it may be the shunt fault, it may be the series fault, it may be the symmetrical fault, it may be the unsymmetrical fault, and how we can analyze the power system during the faulty condition, how we can find out the value of fault current and the fault MVA whenever the symmetrical fault occur or whenever the unsymmetrical fault occur into the power system. So always remember, in every type of fault, whether it is a symmetrical fault or the unsymmetrical fault, the positive sequence current always flow. The negative sequence current flow only when the fault is unsymmetrical in nature. It flow only when it is unsymmetrical in nature. And the zero sequence current will be flow when the ground is involved in the fault. Clear? So now the 2-minute summary. The positive sequence current flow in all type of fault. Flows in all type of fault. Whether it is a 3-phase fault, line to ground fault, line to line fault, double line to ground fault. But the negative sequence current flow when fault is unsymmetrical. That means for the symmetrical fault, the negative sequence current does not flow. And the zero sequence current will flow when ground is involved in the fault, like line to ground fault, double line to ground fault. In fault. Clear? So this is all about the fault, a brief introduction of the fault. Now let me tell you, the Unity is a website, and through this software we can conduct the interactive poll. The 3D model library is there, the class notes and doubt is there. You can ask the live doubt. A video call is also possible. So just unity.pw.live, just log into this and you will get the your leaderboard and the dashboard here. So this is the new software that is developed by the PW for the YouTube classes. So thank you everyone. So now you have a brief idea how to get the value of fault current and the fault MVA for any type of fault into the power system. Just practice more and more questions, so you will be expert to get the value of fault current and the fault MVA. Thank you.